This is lesson 15 of our no-nonsense physics lessons, Whiteboard Physics. This one's all about energy levels and spectra. Well, let's start with what a spectrum is. We can produce a spectrum of light in a few different ways, and one way is to use a glass prism. Now, you may remember from GCSE level that when light passes through glass or any medium, it can refract. So if I have white light coming in, let's use a straight line tool. If I have white light passing into this glass prism, well, the red light gets slowed down less, and therefore it will refract less than the blue light and, well, all the other colors. So the red light might follow a path a bit like that. The green light might follow a path that's a little bit larger of an angle, and the blue light might follow a path which is larger still. And that's because we get more refraction for the blue than we do for the red, because the blue is slowed down by more than the red. And so this is a very well-known phenomenon, dispersion, happening because the refractive index of the glass is slightly different for the different colors. Right, so let's write some labels on this so that we can use this for revision. Let's put glass prism, and then we can have dispersion. And we end up with a spectrum. Let's have white light going in, white light. Now that's one way of doing it. Now what if I had not white light, but particular wavelengths of light because of what we looked at last session, which was the photons that are emitted from the de-excitation only having certain energies because there are only certain de-excitation energies for atoms or molecules or anything else. Well, in that case, it won't be white light coming in. It will be a mixture of the colors that are possible, and or the colors that can possibly be emitted from some sort of source of light, some atoms that get excited. So when they de-excite, they emit a particular spectrum. That means a particular array, a particular assortment of different photon energies and therefore different wavelengths of electromagnetic radiation. So I suppose we should probably define what a spectrum is. Spectrum, if I spell it right, is the singular. Spectrum is the singular of spectra, which is a collection, an array, an assortment. Not sure what I'd describe it as. Spectrum, I'll just say they are the colors of light, colors of light emitted from a source. So a white light spectrum emits all of the possible colors, but in this case, we're looking at quantum phenomena because there are certain excitation energies that we get what's called a discrete spectrum. So a hot body might produce a continuous spectrum. Hot bodies, such as if you take a piece of metal and you heat it up so it glows, you'll get a continuous spectrum. Continuous spectrum. But what we've got here is the de-excitation of a body. So de-excitation, that's going to cause what's called a discrete spectrum. And a discrete spectrum only has certain colors of light. And that's because there are certain de-excitation energies. So let's make a note of that. Certain colors because there are certain let's just call them excitation energies. Excitation energies. Okay, that's quite important. That's what makes it a quantum phenomenon, the fact that there are certain values of photon energy. Therefore, certain values of photon energy. That's why it's a quantum phenomenon, because there are certain values. Okay, so we need to have a little bit of understanding about this spectrum, I guess. We could talk about the rough wavelengths of these colors. So red is somewhere a little bit less than 700 nanometers. That's the extreme end of red. The extreme end of violet would be perhaps 350, although we usually say 400 nanometers for that. 400 nanometers for a violet color. Purple, as everyone else would call it. About sort of 530 nanometers somewhere is green in the middle. So let's put that there. 530-ish nanometers would be green. And it's good to have some sort of understanding of this. Now, these are wavelengths. And we know the relationship between the wavelength and the frequency. So remember that the wavelength is going to be, let's try and draw that better, that's the lambda symbol. Wavelengths are going to be equal to the speed of light divided by the frequency. And we also know that E is equal to HF for our photons, where E is the excitation energy. And we've covered that before. E is equal to HF, and therefore is equal to HC over lambda. So it all ties together, where E is the excitation energy, or the de-excitation energy. Excitation energy. Because there are different excitation energies that are possible, and H and C are constant, there are different wavelengths that are possible, right? So we want to produce a line spectrum. That's what we can call an array of different lines, a line spectrum. So let's make a new title, producing a line spectrum. And what is a line spectrum? Well, it is just a spectrum of colors where each color is represented by a single line. That's all it is. It's nothing more complicated than that. So what we can do is we can use a light source, and I will represent that as maybe some sort of container of gas. And they're going to say it's excited somehow. Maybe we put a big potential difference across it or something like that. That's going to emit light in all directions. So what we can do is we can choose to use the light in one particular direction. So we use a single slit, and it's that slit that causes us to have a spectrum of lines, a vertical slit will produce vertical lines. And then we can use some sort of telescope, microscope. We usually call it a collimator. Collimator. And what that does is that causes the light to all go in straight lines. And now we can do a few different things here. We're just going to stick with the prism, which is going to refract the light, and then we're going to have a microscope that we can move around in an arc. And we can move that around in an arc in both directions and measure the angle between what's going straight through and where we see the light. So we can measure that angle. And there's our microscope. And then we just place our eye on the end of this. Now, as we move our microscope around that angle, what we will see is a spectrum of lines, the images of the slit. So you might have sort of red line there. There may be a yellow line, but they'll be discrete. There'll be gaps between them. You might get a few green lines, perhaps. It depends on what you're looking at. Maybe a bit of a blue line, and then you might get a purple line. And of course, there will be lines that you can't see. But because you can't see them, we can't draw them. They're invisible light, infrared, ultraviolet, that sort of thing. So this is what's called an emission spectrum. And it's called an emission spectrum because we're looking at the light that is emitted from an excited gas. And it is also called a line spectrum because it's a spectrum of lines. Now, there is something called an absorption spectrum, where if you shine white light through a gas, it can cause excitation at certain energies and scatter that light so that it's not traveling straight through. Now, if you do that, you'll see a continuous spectrum, but dark lines. And those dark lines, the absence, or at least the less intense radiation of those particular wavelengths, they will correspond to the lines on an emission spectrum caused by an excited gas. So we can use absorption spectra and emission spectra together to analyze the composition of a gas. Let's just say, use to analyze composition of gas. This is called spectrometry. That's not how you spell spec. Come on, handwriting. Spectrometry. Metry means measurement, and spectro is a spectrum. We're measuring the spectrum, spectrometry. So that's what we're doing. Some spectrometry, emission spectrometry. And the instrument that we can use, which has the collimator and the microscope and a platform to place a prism or anything else that causes diffraction, the slit, and it all has a scale that we can use to measure the angle between the collimator and the microscope. That's called a spectrometer, because it's the instrument we use for spectrometry. But that will come up later when we look at waves and we learn an equation for the diffraction. Anyway, we already know that the excitation energy, I should probably point out somewhere that is the difference between energy levels, but that's from the previous lesson. So I'll just leave that there. It's caused by electrons moving down an energy level. And I don't know if there's anything else I really need to say. We've already talked about the Bohr model of the atom, and we've talked about the hydrogen equation. So you can produce a hydrogen spectrum. So let's just have a look at the hydrogen spectrum. Hydrogen spectrum. So the hydrogen spectrum, remember we have our equation for energy levels from the last lesson, which was that the energy level, and let's just scroll a little bit to make this work. I'm on line mode. The energy level is equal to, it was 13.6 electron volts divided by n squared. So we were able to produce our energy level diagram, and I'll do that here with just a few levels. I'm not going to do loads of them. We've got n equals 1, and that is at negative 13.6 electron volts. And then let's get my calculator out to do the rest of the calculations. I think I'd have these memorized by now, wouldn't you? Divide by 4, so then we have n equals 2, which is at negative 3.4 electron volts. We've talked about what these mean. N equals 3, so that is 13.6 divided by 9 is negative 1.51 electron volts. I'm not being very consistent with significant figures here. N equals 4, so it's 13.6 divided by 16, negative 0.85 electron volts. And we have different transitions that are possible. So we can go from n equals 4 straight down to n equals 1. We can go from n equals 3 straight down to n equals 1. We can go from n equals 2 straight down to n equals 1. We can go from n equals 4 down to n equals 3. And we can go from n equals 2, sorry, and n equals 3 down to n equals 2. And we can also go from n equals 4 to n equals 3. And so you can see that there are 6 possible de-excitation transitions. And each of those 6 transitions corresponds to a particular wavelength of light. Let's just number them 1, 2, 3, 4, 5, and 6. And let's do some calculations. So, and I'm not going to do it for all of them, but we'll start with 1. Transition 1 is a difference in energy of from negative 0.85 electron volts to negative 13.6 electron volts. So we will have, let's do 13.6 subtract 0.85, we will have 12.75 electron volts of energy in that photon. Okay, well, let's convert that into joules by multiplying. So 12.75 multiplied by 1.60 times 10 to the negative 19 is going to give us the same amount of energy in joules. That's 2.04 times 10 to the negative 18 joules. Okay, so that's stage 1, that's stage 2. What's stage 3? Well, now we've got the energy in joules, we're going to use E equals hc over lambda, and say that lambda is going to equal E equals hc over lambda, so hc over E. And so that's going to be 6 point, now I need to remember what this is. My memory is so bad for these things. 6.63 times 10 to the negative 34. 6.63 times 10 to the negative 34 is Planck's constant, times 3 times 10 to the 8, and divide that by our energy of the photon in joules. So if we do that, reciprocal of that times 6.63, I'm just typing it into my calculator, you can't see what I'm doing. 3 times 10 to the 8. And that gives me 97.5 nanometers. Now that's ultraviolet. We can't see that one. So that transition is invisible. We could do the same thing for transition 2 and transition 3, but let's just have a look at transition 4. We won't do them all because we'll be here all day and you'll watch me do 6 calculations, which is a bit pointless. So difference in energy. negative 0.85 minus negative 3.4, and that's in electron volts. So that gives you, let's go 3.4 subtract 0.85, 2.55 electron volts. So that's obviously much less. Now we're going to turn that into joules. Do not forget that step. Oops. So that would be 1.6 times 10 to the 19 minus times. So that gives us 4.08 times 10 to the negative 19 joules. And then the last step, which was to do 6.63 times 10 to the negative 34 times the speed of light times 10 to the 8, all divided by that amount of energy in joules. So like that, which will give us the wavelength. So 6.63 times 10 to the 34 negative, 3 times 10 to the 8. That gives us about 487.5 nanometers. That is visible. That's going to be towards the bluer end of the spectrum. Somewhere between, somewhere between green and blue. So towards the bluer end of the spectrum. And so on and so on. So that's a visible transition. And we can analyze all the transitions and see which are visible, which are not. Or we can extract light from the excitation of a gas and look at the discrete wavelengths we get, it's called spectrometry, and work backwards to work out what the energy levels would be to give you that particular spectrum. Once you've got that spectrum of energy levels, you can see what gas it is. Now, this was done for light from the sun, although we have to use an absorption spectrum, not an emission spectrum. But the light that comes from the sun, from the photosphere of the sun, is a continuous spectrum. And we pass that continuous spectrum through the atmosphere of the sun for the light to reach the Earth. And when we pass the light from the sun through our spectrometer, we find dark lines, an absorption spectrum. And some of those dark lines correspond to the bright line wavelengths, an emission spectrum for hydrogen. In fact, most of them did. So we knew that the sun's atmosphere contained hydrogen. But there was another gas that we could not identify. There were absorption lines that corresponded to colors that we had not seen in an emission spectrum on Earth. And this was something of a mystery. And it turns out that this element is helium. We named it helium after the Greek word helios, meaning the sun, and because that's where it was first discovered. But then we discovered helium on Earth and found that, yes, indeed, helium was the gas that was found first in the sun before it was found on Earth. So I will stop there. We've covered, I think, what we needed to cover about energy levels and spectra and the use of this particular quantum phenomenon. And next lesson, we are going to look at the more tricky topic of wave-particle duality.